It's a pleasure to be here. As a brief introduction, I am a professor of physics and astronomy at the University of Maine. I got my PhD in general relativity, and the neat thing about that is that the first talk I ever gave was to Stephen Hawking and his group at Cambridge. And that was an interesting experience, to say the least. I have been here at the university for 42 years. I started writing books in 1993 when my older son, James, started asking what if questions, and that led me to ask what if questions. And the first question I asked was, what if the moon didn't exist? And that's what I'm going to be talking about now. So why don't I get started? And I will be doing this all entirely just me rather than screen sharing. And hopefully that will be sufficient. So the way that I think is to do this most effectively is not to tell you what would be like if the moon didn't exist, but rather to explore how the Earth got to where it is today. And by doing that, I hope it'll, when we get to the end and take away some of the effects that the moon causes, or all the effects that the moon causes, it'll become hopefully clear what the Earth would be like without the moon. Okay, so that's the background. The solar system, which is the sun and everything that orbits it, formed about 4.6 billion with a B years ago. And it was essentially a cloud of gas and dust that began to collapse due to its own gravity, the interaction between the gas and dust, that pulled everything together. And among the planets, the Earth formed. It is, as you know, mostly rock and metal. And of course, there's water now and an atmosphere. But when it first formed, it was very hot because it was condensing gases and dust that were colliding with each other to form a bigger and bigger chunk of real estate, namely the Earth. And so when the Earth was young, it was very, very hot due to the collisions of all the particles that were hitting it. And at the same time, it was spinning, but we don't know how fast. I mean, it spins today, of course. That's why we have day and night. And as the Earth was spinning, and so, you know, we pick a number, maybe 10 times faster than it is today, or 5 times faster is probably the operant phrase here. So it was spinning, and there was a lot of other debris flying around in the very, very young solar system. And the current theory is that there was, among other things, a Mars-sized piece of space debris, really big, of course. And it wasn't orbiting in a nice, nearly circular orbit like Mars is today, but rather it was in a very elongated orbit. And that orbit crossed the Earth's path. And when that happened, the two bodies collided. And just for reference, the mass of Mars is about 1/10 the mass of the Earth. So this is an object that hit the Earth around 1/10 as big as the Earth itself. And that impact, we believe, splashed debris into orbit around the Earth. And that debris was mostly material that came off of the Earth's outer layer. And actually, as a result of that, the Earth had a ring, like Saturn, had a ring before it had the moon. And so there was a ring, and calculations suggested lasted for maybe 100 years. And as a result of collisions between the orbiting bodies, these are pieces of dust and rock and boulders orbiting around the Earth, as a result of this collision, this debris started colliding with itself, and one chunk of it got bigger and bigger and bigger by pulling other stuff onto it, gravity, until an object, the moon, was formed. Okay, so that's step one. But the thing is that we know for absolute sure that the moon, when it formed, was not as far away from the Earth as it is today. To be exact, we don't know how close the very, very young moon was, but we can hypothesize, based on things that will become clear in a moment, we can hypothesize that the moon, when it first formed, was around, ballpark figure, 10 times closer than it is today. Should make it quite a big object in the sky. But more important than big, its force of gravity on the Earth would have been much greater, and 100 times greater. And it turns out that, and this is the thing that I'll explain next, it turns out that the tides created by the young moon, when it was 10 times closer, the tides were 1,000 times higher than they are today. So let me explain how tides work, because a lot of the places where you read about tides, including some of the astronomy textbooks, get it wrong. So this is how tides work. And if you're interested, there's a website, a NOAA, N-O-A-A website called Our Restless Tides that can explain how the tides work in the detail that I don't have time to do, but I will give you the concept. Okay, so first of all, as I'm sure you can well imagine, if this is the Earth and this is the moon, the force of gravity from the moon on the Earth, as you get farther away from the moon, the force of gravity goes down. So the force of gravity on this side of the Earth is highest from the moon, and the force of gravity from the moon on this side is lowest. Okay, so that's a change in the force of gravity. And it was often said by speakers and television people, even astronomers who explain the force of gravity, they said, and this is wrong, they said that the force of gravity, because it gets weaker, which it does, okay, on this side, on the moon side of the Earth, the water was pulled up. The Earth was pulled less because it was farther from the moon than this water, and the water on this side was left behind. If you ever see that or read about that, that's wrong. So let me explain what's right. It turns out there's a common belief that the moon orbits the Earth. Makes sense, of course, we see it go around, but in fact, that's not true. The moon doesn't orbit the Earth. Rather, the two bodies are, as the moon orbits, we also orbit. The two bodies orbit a common, we call it a center of mass. Think of two dancers holding hands, holding each other and spinning around as they go down the dance floor back in the old days. Well, if you were to follow each of them, they would both be going around, but there would be a point between them. If they were going in a straight line, there would be a point between them that went in a straight line down the dance floor. So the two would be going like this, and the straight line between them is called their center of mass. The Earth and moon have a center of mass. So this is now the moon still, and this is the Earth. And as they waltz together, there is a point, and it's 1,067 miles under the Earth's surface. So it's not the center, 1,067 miles under the Earth's surface that the two bodies orbit together. And the so what about that is that as the Earth is going around, well, think of if you're on a merry-go-round, especially one that's going quickly, As you go round and round, you feel a force from the merry-go-round. And of course, that force is pushing you away from the center. I remember when I was a kid, I was on a merry-go-round once, and somebody started spinning it so fast that I couldn't hold on, I flew off. And that concept of being pushed out as the earth goes around and around, the water on the earth feels the merry-go-round effect. And so as the earth is going around, here's the moon, here's the earth, as the earth is going around, this motion around the center of mass pushes the water, all the water on earth, away from the moon. So in this motion, all the water on earth is being pushed away from the moon all the time as the two bodies orbit the center of mass. And so now we have two players in the game of what creates tides. Number one, the force of gravity is getting weaker and weaker. So the force of gravity on this side is strongest. And the force of gravity over here is lowest. And at the same time, there is a universal repulsion of all the water is being pushed away from the moon by this motion around the center of mass. So gravity pulls towards the moon, the water, and this motion pushes all the water away from the moon. And so then the question is, who wins? And the answer is, it depends on which side you are on. So on the moon side of the earth, okay, the force of gravity from the moon is stronger.
There's still, at the same time, I hate for us to lose sight of them.
I'm sorry, say again, please. I couldn't hear. Or maybe that wasn't a question. Well, let me go on, but if there was a question, don't hesitate to ask. The water on the moon side, okay, feels the gravity from the moon and the force away due to this outward force. On the moon side, the water is pulled by gravity. Gravity from the moon wins and pulls this water towards the moon. On the other side, on this side over here, the farther side from the moon, this motion wins, pushing the water away from the moon. So there are two forces of gravity. The two forces creating the tides, gravity and the rotational outward force. On this side, gravity from the moon wins. On this side, the outward force wins. And therefore, no surprise from hopefully from what I just said, there are two high tides on the earth all the time. One on the side closest to the moon, and the other on the side opposite the moon. So that is the big picture of how tides are created. And they were created back in the day when the moon was 10 times closer than it is now. As a result of that, as I said before, the tides then, when the earth and moon were young, were 1,000 times higher than they are today. Well, here in Maine, we have tides that can go up to 40 or 50 feet high. And if it's 1,000 times higher, that's considerable amount of water moving in and out. And so let's keep that in mind as we proceed here. Okay, so we now have tides, two high tides. And then on the up around here is where the tide is lowest. So high tides and then low tide around there. Okay, now the moon, as you all know, is orbiting with the earth around the center of mass. But the earth is also spinning on its axis. This is what causes day and night. And the earth is spinning much faster than the moon and earth are orbiting around the center of mass. So as the moon is orbiting and the earth is orbiting, the earth is spinning much faster than this orbit. And the so what about that is that the high tide created by the moon here, and let's just focus on this one for simplicity, this high tide is not in a straight line between the center of the Earth and the center of the moon. Rather, because the Earth is spinning fast, the high tide created by the moon is about today 10 degrees ahead of the moon in its orbit. So this is what the system looks like. The high tide staying about 10 degrees ahead of the moon. And the Earth spinning, of course, once a day. So we'll get back to what happens as the high tide moves over the Earth, which it does. But let's stay with the high tide here for just a second and look at its effects on the moon. So this is water, lots of water. And back in the day when the tide was, several thousand feet high, miles high, okay, there was a lot of water here pulling on the moon because the water here has gravity just like the rest of the Earth does. But this gravity from this water pulling on the moon is not pulling the moon straight towards the Earth, where the rest of the Earth is trying to pull the moon towards it, and they don't collide because they're moving around. But this water is not pulling the moon straight towards the Earth, it's pulling the moon forward in its orbit. You can think of this as, suppose you had a ball on a string hanging straight down, and then you started spinning around. Well, you know what would happen? The ball would move out, essentially spiral away until the string was out here if you're moving around fast enough. Well, that's what's happening to the moon. This water is pulling on the moon, giving the moon energy. Just like when you're pulling on this, when you're spinning around with that string, you give the ball that's hanging down energy, and that causes it to spin around and spiral out. The moon is doing the same thing. The moon is spiraling away from the Earth because of the energy it gets from this high tide, which is kind of interesting. And another common mistake that's made by people who present this information is that they say, well, the moon is given energy from the high tide, which it is, and therefore the moon is spiraling away with more and more energy, going faster and faster all the time. That's wrong. The moon is spiraling away, but as it does, it slows down. It's slowing down because the energy given to it by this water is given to it so that it can move out, not fast. And so the moon is spiraling away, and, well, as I just said, the Earth gives the moon energy to make it spiral away. But you can't get something for nothing. That energy has to come from somewhere. And the energy that the Earth gives to the moon comes from the Earth's rotation. The Earth, okay, well, let's look at this now. Here's the high tide. The Earth is spinning once a day. The high tide is just a few degrees ahead of the moon. Therefore, this water, to stay in this position here, has to slide over the Earth's surface. So as the Earth is spinning, the water is going like that. And as the water of the high tide moves along the Earth's surface, there is friction between them. And the friction between the water and the surface of the solid parts of the Earth, like if there's a high tide going across the Atlantic Ocean, for example, then it hits or bumps into these nasty continents, North and South America, and the interaction between the water and the continent causes the Earth's rotation to slow down. So that's the next point to make, is that while the moon is moving away, farther away, slower all the time, the Earth's rotation is also going down. As I said, we don't know for sure how fast the Earth was forming, how fast the Earth was spinning, excuse me. things are changing on the screen here, so I'm not sure what's going on, but I'll just keep talking until I hear otherwise. The rotation of the Earth is decreasing. We don't know how fast it was, but of course today it spins around about once every 24 hours. That's our day and night. So back in the day, the length of the day might have been, round numbers, 10 hours long, picking a number. And so the presence of the moon has caused the Earth's rotation rate to slow down. And that process continues today. In fact, how do we know this is true? Well, the astronauts, Apollo 12, I think, maybe Apollo 11 too, they brought onto the moon an experiment to test what I just said, to see if the moon is really spiraling away from the Earth. And they put on the moon what are called corner reflectors. Now, that may not quite mean anything, but think about this. If you're in a car at night, you have the headlights on, and another car is going along or is parked, okay? You can see that other car, even if it doesn't have any lights on, because your headlights hit the red or orange plastic things, which you can see in any car. And what happens on Earth is that the light from your car hits what are called, they're called corner reflectors. And what happens is that they, if you could imagine, I'll just move this for a second, the corner of a room there, okay? And then think of the path of light from your car hitting that corner in the little red or orange plastic thing. So take a look at them sometime. You'll see that they, each of these corner reflectors have lots and lots of little squared off edges. The light comes in, and what happens is that the light hits one edge, the second edge, and the third edge. And when it hits the third edge, it reflects off of it and comes straight back to you. And therefore, your headlights illuminating the corner reflectors in a car or other object tell you it's there so that you don't hit it, or that, you know, give you an idea of the direction it's moving. Well, they took the corner reflector concept and put it on the moon. So today they're still there. And what has happened since then, since the astronauts walked on the moon, is that here on Earth, people, and you can do this, I mean, this is, you know, an experiment that's eminently doable with our technology. You take what they did, and what they do is they take laser beams and they fire a laser beam at the corner reflectors on the moon. And the light from the laser beam hits the corner reflectors, one edge, then the second edge, then the third edge, and is reflected back to the source of the laser beam. And if you have a detector, excuse me, if you have a detector next to your laser beam, you can actually see a glow from the moon with your light sensitive detector. That is the reflection of your laser beam. And the thing to do is to time the round trip. How long does it take for the light to go from you to the moon and back? And the answer in round numbers is about 2 seconds. Very measurable. And it can be measured with great precision today. We have, you know, excellent equipment for that. And so what they have done since the 60s, when the astronauts were on the moon, is they have timed the round trip to the moon and back. And every day, every year, every decade, the round trip time gets longer and longer and longer. Why? Because the moon is spiraling away, or the Earth and moon are spiraling away from each other. And so the moon, we experimentally know, is spiraling away and has been doing so ever since it first formed. excuse me. And that is, an incredibly important piece of this puzzle. So the thing to do, well, the obvious thing is, okay, if it's spiraling away, is it going to someday leave the Earth's orbit forever? Reasonable question. And the answer is absolutely not intuitive. No, it's not. The moon is never going to leave the Earth's orbit unless something strikes it and knocks it away, which is not too likely, but one never knows. Anyways, the reason it's not going to leave the Earth's orbit is because as the moon is spiraling away, the Earth's rotation rate is slowing down. And in about 20, if memory serves, it's about 20 billion with a B years from now, the Earth is going to be rotating, spinning so slowly that the rotation rate of the Earth and the orbital rate of the moon around the center of mass will be exactly the same. So in about 20 billion years, the system is going to go like this, and the high tide closest to the moon will indeed be in a straight line between the two bodies. It won't be ahead, and therefore this high tide cannot give the moon any energy anymore when the two are going like this. And from then on, the moon will not spiral away from the Earth. There's another aspect of this you should know. In about 5 billion years, the sun is going to blow up, so it really doesn't matter anyways. But anyway, that's just another piece of scientific information. Okay, so we now have the real situation of the high tides created by the moon and the Earth orbiting together, and their interactions and the effects that those high tides have on the Earth, slowing the rotation, but also all the other things that the high tides do, which is, things that are sometimes very exciting. As I say, here in Maine, it's amazing to go between high tides and just watch. You can literally watch the water going down if you have a time delay camera. Sometimes when I do television shows, I take the crew to a place where the tides are huge and the water is splashing up, and they put a time-lapse photograph and watch the water going down and then back up again. So it's an interesting thing. That, let's think about this for a second here. Real life still. The high tide when the Earth was young, 10,000 feet high, I'm picking a number, round number, 10,000 feet high, and it was going inland and out every 2 hours. Real life now, this is still real life. And when you think about the consequences of this huge amount of water going in for miles really fast, and then coming back out again, what that water is doing is it's grinding the surface. It is wearing the surface, eroding the surface due to the tremendous amount of pressure and changing motion of the water. And so the water from the Earth, the high tide, wore down the continents near the oceans, of course, and that had the effect of putting a lot of the rocky debris into the oceans. And the so what about that is that is what initialized what we call the primordial soup. Now, there is a second way that rocky stuff gets into the ocean, and that's through volcanic vents. Absolutely true. But back in the day, the primary source of getting material into the oceans so that life could form was through the erosion of the continents due to the high tides. And as you all know, that's going on today, the erosion, but not nearly as much as it was back then. And so I think we've gotten to the point where we can now say, okay, well, what if the moon never existed? What if the moon didn't exist? And look at the consequences, because I hopefully have given enough background information to help us quickly figure this out. Okay. Actually, no, there's one more thing. I'll mention it as we go. But the first point I would like to make is that if the moon had never existed, the Earth would be spinning faster. No surprise there, because it was back in the day. And the amount of debris getting into the oceans from the land would have been much, 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 much less than it has occurred on Earth and is still occurring today from the volcanic vents. So what? Well, the so what is, I would hypothesize that under those circumstances, the quote unquote primordial soup from which life formed would not have been enriched in the oceans enough for life to have formed as early as it did and to persist. In other words, it is entirely possible that in a volcanic vent on the Earth that never had a moon, there was debris coming out of the Earth and would have provided the primordial soup in that area. And life could have formed around there. But if there wasn't the same kind of debris for hundreds or thousands of miles surrounding it, that life could only have existed near that vent. And if the motion of the water pushed the life away, it could never have replicated. So there might have been local regions of life on Earth, but not the global explosion of life in the oceans due to this very rich primordial soup, driven in large measure by the presence of the moon. So I would sum that up by saying I believe it is very unlikely that advanced life, meaning even fish, could have evolved as early as they did, and therefore life going from the oceans to the land, as is believed to have happened, would not have happened nearly as rapidly. In fact, it might have taken billions of years longer for life to have evolved onto the surface of the Earth than did happen, because there wasn't the primordial soup available. So that's a big if. We wouldn't be here yet. We might not be here for another few billion years if that had been the case. Another consequence of the rapidly rotating Earth is that the winds would have been profoundly different. Now, winds it's complicated, and people spend their entire career, some meteorologists spend their entire career studying the winds. But big picture is that when the sun heats the surface of the Earth and the gases in the Earth rise and sink, and there's rain and other activities, this motion of the gases of the Earth due to heating and cooling and the rotation of the Earth lead to the wind and essentially the weather that we have. So if the Earth had been rotating much faster, that cycle of heating and cooling from the sun and the motion of the gases in our air as the Earth is spinning around faster and faster would have been profoundly different than they are today. Therefore, it's extremely likely that the weather would not be anything remotely like it is today, and probably much less user-friendly, which is to say that there probably would have been much higher winds, and the storms and other activities, I mean, it would have been very complicated. It can be synthesized or reproduced on computer, but I don't know if anyone has ever done that. But the point is, the weather would have been very different than it is now. So let's assume for conversation that the winds would have been significantly higher because of the rapid rotation of the Earth. It would then follow that the evolution of plant life would be very different than it is here. And the reason is because the trees and bushes and everything else, they have to withstand the winds or they're not going to survive. So it is likely then that there would not be high trees. They would be lower to the earth. They would be more spread out, perhaps with a much more substantial root system than many plants and trees have today. And therefore, if there had not been the high trees that did in fact exist on Earth, then the animal life that evolved would not have been the same. There would not have been chimpanzees swinging from branch to branch on high trees. The animals on this world, of the rapidly rotating windy world, would have had to have been lower to the earth. They would have had to have been able to stay there with the winds blowing, if that is the correct model. And they would never have evolved anything like us. Turtles would do very well. Snakes, perhaps. But tall, slender creatures like ourselves in winds that are normally, let me pick a number, 50 miles an hour, not too likely. So the animal life on the earth without the moon would have also been profoundly different than it is today. Plant life different because of the winds, animal life different because of where it would have developed compared to where human life developed on Earth. And so we wouldn't be communicating the way we are. In fact, it is an interesting question if, for example, fingers, hands had not evolved because the creatures had to dig into the soil with all four to stay there. How advanced could that life have evolved to become? Are we lucky among many, many other reasons because we're able to evolve the things that we have, both the brains and our senses and our appendages, and use them as we do. So the whole thing, it changes virtually everything. And I think I'll stop there. And if people have questions, I'd be more than happy to answer them. And thank you for listening and viewing.
Wow, that was phenomenal. I know that we have a question right here from Joel Weinberger, who's been listening intently.
Hi, Neil, winner of the Joel Weinberger Lookalike Contest.
Thank you.
Thank you.
I have a million questions, so I don't want to eat up all the time. So I was going to ask you a bunch of questions about what happens when the moon reaches its maximum orbit and the Earth stuff, but it doesn't matter. If I heard you had a throwaway line, the sun will explode by then, so who the hell cares? Was I right in hearing that?
Yes, you were.
Okay, so what will since I'm stubborn and won't give up my questions, what about 4.5 billion years from now? What would the Earth and the moon look like? The Earth would be much slower in its spin.
Yes.
The moon would be much further away. The tides would be more flat, I would imagine. And what would that mean?
Well, it would certainly mean that the moon, as seen from the Earth, would be a substantially smaller object in the sky. there would never in that time be what we call a total solar eclipse, which is to say the moon today is almost exactly the same size in the sky as the sun. So today, the moon can move right in front of the sun and completely block it, just barely. As it gets farther away, it's going to get smaller as seen from Earth, but the sun is not. So there will never be a total solar eclipse again. The tidal change is going to have, I would expect, a substantial effect on the life forms on the boundary, in the oceans, on the boundary near the shore, if you will. And I think that that is going to be a slow evolutionary change given how long it takes for this process to occur. But I would expect that there would be a substantial change in the surface life, especially near the shore, both in the water and on the land. So those are some things that come right to mind.
What about day and night? Wouldn't they be different?
Oh, yes, thank you. You got the obvious one. That's great. Yes, the Earth would be spinning slower, and therefore the day would be longer and the night would be longer, which raises a really interesting point. I'm so glad you asked that. And that is that humans and other animals have built-in clocks, biological clocks, that synchronize our awakeness to the day-night cycle. In other words, when we wake up, our biological clocks, and you probably know more about this than I do, Joel.
Don't bet on it.
Cause us, our bodies to start doing activity that is appropriate for daytime, awake activity. And at night, our biological clocks help our bodies shut down so we can sleep. And it turns out that the biological clocks that we have to be tuned to within about half an hour, if memory serves, of the 24-hour cycle. So that if, for example, you were on the space station today and they didn't have day and night, lights on, lights off, in a 24-hour cycle, you would very quickly become completely disoriented and unable to function well. And that's been shown in other conditions, like in mines, for example, that how important it is to have the day-night cycle. Well, to your question, when the moon is moved farther away and the day is much, much longer, we humans, as we are today, would not be able to function there. So hopefully, there would be an evolution in our biological clocks as the time grows longer so that we can adjust and function on an Earth with a much longer day. How about that?
That works. I've got more, but I don't want to interrupt people.
We do have another question.
Okay.
Can you tell us more about the sun blowing up? This is a question from somebody who's on with mute on.
Sure. Yes. The sun shines today because in its very center, the force of gravity of all the gases that is the sun, there is no solid part of the sun, by the way. The force of gravity of all the gases that are the sun are compressing the sun so much that in its center, the particles, protons, neutrons, and electrons, the particles are being forced together. It's a process called thermonuclear fusion. And this process of, if you can do it, and it takes a lot of energy to force particles to stick, but if you can do that, then that process releases energy, and that energy that is released by fusion in the sun, that energy eventually comes to the surface. I won't go through the details for time constraints, comes to the surface and then flies away into space, and we call it sunshine. The punchline is that this process is changing the chemistry of the sun. And the chemistry of the sun, which was mostly hydrogen and helium, is becoming more helium rich. That's the things that hydrogen fuses into. And then another cycle later, the helium is going to fuse into carbon. And so now you're going to have a center of the much older sun, which has a different chemistry than the sun does today. And surrounding this central core of carbon stuff are going to be shells of hydrogen and helium that will then begin fusing by themselves, because gravity is pushing in on the outer center, the outer core of the sun. And when this outer layer starts fusing due to the gravity of the sun pushing in on itself, the energy released by the fusion out here, not from the center, but out here, this fusion energy, same amount of energy that was created in the center, but out here, it has enough energy to expand the outer layers out and blow them into space. And it's going to be a wimpy explosion compared to what we call a supernova, but nevertheless, the outer layers are going to blow off, the core of carbon is going to stay there, and the planets, especially the inner planets like us, we're toast.
Literally.
Yes. I hope that answers the question.
More for me.
I don't know, the person is muted. You can unmute yourself if you have a question for Neil. Feel free to unmute yourself and ask a question.
I'm going to ask a question here for our audience. There are a couple of us listening. Why do we see the moon out in the morning sometimes? And sometimes it's more visible than others.
Excellent question. The answer is because as I said earlier, the moon orbits the Earth much more slowly than the Earth is spinning. So let's take, here's my glass of water that I was drinking from before. This is now the sun, okay? When the moon is between the Earth, here's the Earth, and when the moon is between the Earth and the sun, okay? We see what is mostly the dark side, because the side that's lit up, oh, my hand is lit up, that's nice. By the sun is the side we cannot see. Now, as the moon, it takes about a month, 28 days, roughly speaking, for the moon to go around, as compared to the sun, for the moon to go around the Earth. So we started here, this is what we call a new moon. We see that it is mostly dark because we're seeing the dark side of it. However, as time goes on, I have to do it this way, as time goes on, the moon is going around, from our point of view here, the moon is going around, and for example here, we would see half of the lit side and half of the dark side. And here, we would see the entire lit side of the moon, because the sunlight strikes it and comes back to us, and we call that a full moon. So new moon, first quarter moon, full moon, third quarter moon, and back again. And the punchline, to answer your question, is that because the moon is in different places as seen from Earth compared to the sun, as the Earth is spinning around, okay, take this situation right here, for example, with a full moon. As the sun is setting with a full moon over on the other side of the Earth, okay, as the sun is setting, the moon is rising. And therefore, when there's a full moon, the rising moon is on the other side of the Earth from the sun, and therefore the moon rises, when it's full, rises at sunset. When it's on the same side of the Earth, of the Earth as the sun is, and the sun sets, the moon goes down with it, because the moon is orbiting very slowly around. And therefore, when it is a new moon and it's dim already, it is setting with the sun. And therefore, we see it go down at about the same time and come up the next day at about the same time as the sun does. And it looks dark in these situations, but when it's rising at sunset and the same full moon here is setting at sunrise, it looks very bright in the sky because it's on the opposite side of the earth from the sun. Did that help?
I think so. I think so. Next time we'll pay more attention to the time when that happens.
Okay, yes.
Thanks.
And of course, if you want, there are diagrams all over the internet that shows the phases of the moon and what times they rise and set. Good question.
Thank you.
I have a question from Susan Jacquette. She is asking regarding moon's effect on biorhythms. I've heard that when girls and women live together as in a dorm, their monthly cycles synchronize. Is this true? And if so, why and how?
That's an excellent question, and I don't know the answer. If anyone does, Joel, do you have any?
No, that's all mystical to me.
Yeah, my apologies. I don't know whether or not that the syncing of biorhythms is in fact has been experimentally shown to be correct. If I find out, I'll let Debbie know and she can share that.
We have a question from Sylvia Baer. Go ahead.
Hi, thank you for doing this. My question was more or less what the last one was, but a little bit less specific. If the moon has such an effect on such massive structures on Earth, why don't we feel that effect as humans? We're little piddly things. Why doesn't it affect us in a very significant sensation way?
That's a fantastic question, and I thought about that when I first started doing this decades ago, excuse me. The answer is that the force of gravity, here's the sun again, or moon, and here's the earth. The force of gravity, if you're standing, okay, here's a human now, this is a human standing on the earth. The force of gravity is stronger here. If the sun is high in the sky, it's strongest on your head, and weaker down at your feet. But the point is that the force of gravity, the difference between the force here and the force here, head, feet, the difference is so slight that the atomic bonds that bind all of our bodily parts together are so much stronger than the difference, and this is the important point, the difference in force between here and there. The bonds that hold us together are so strong that the difference in force due to the moon or the sun is not high enough or not strong enough to stretch us apart in any measurable way. It's just the difference in force from head to toe is just too weak to do that.
Okay, thank you.
Sure, good question.
Any other questions? Yes. Joel has one. If no one else is going to, I'll give a second for someone else who might have a question. Okay, go ahead, Joel.
Okay, first I apologize for all these questions. My mind is racing on all of this. So I heard you say, I want to make sure I heard it right, that thanks to the moon, life evolved on the earth much sooner than it otherwise would have. So that suggests to me we're looking for life elsewhere in the universe, and I always hear Earth-like planets. ought we not to also be therefore looking not just for Earth-like planets, but Earth-like planets that have a moon revolving around them?
The short answer is yes. I've actually thought about that also in the context of what we call exoplanets. And I believe that that is a very reasonable thing to look for. We're getting to the point where we can start detecting moons by their gravitational effect on their worlds. I'm not sure we're there yet, but it's getting really close. And that would certainly be a factor. And it could be, okay, so that's the short answer. The slightly longer answer is different size stars, like the sun, different size stars have different lifetimes. The more massive, totally counterintuitive, the more massive a star is, the shorter its lifetime. So when we look at planets orbiting cooler, less massive stars than the sun, those stars can last so long, and they may have been out there so long, that life could have evolved on those Earth-like planets even without a moon, and that could well happen before that star's going to blow up. So, you know, if you're looking at the Earth-Sun system out there in space, I would say definitely look for a moon. But for cooler stars and Earth-like planets, those stars and planets will last long enough that it's entirely possible that life would have evolved well before the star dies.
Got it.
Right.
Do we have another one before Joel asks another question? Okay, Joel, go ahead.
Sorry.
No,
Neil,
no.
early on you talked about that the center of gravity is not the center of the Earth. It's like 1,000. Is that just because the Earth is somehow lumpy and that's where the mass, no?
No, the Earth spinning, it's not perfectly spherical, and there are mountains, of course, sticking up too. But the point is that no matter what shape the Earth is or the moon is, the two bodies are going to be orbiting a common center of mass. And in the case of the Earth, which is quite, if you look at it from space, quite circular, quite nearly spherical, that motion of the Earth has nothing to do with the shape, just the masses of these two bodies and how far apart they are from each other.
Got it. I'm going to shut up.
Any other questions from anyone? I know we have quite a few people on, so please unmute yourself and ask. Sylvia, I see you're unmuted. Would you like to ask a question?
No, I'm trying to wrap my brain around all of this. I'm a literature professor. It takes us a while. So I thank you for doing this because it really is incredibly helpful. Thank you.
Oh, I'm honored that you feel that way. Thank you very much. And if you have questions, don't hesitate to get in touch with me. My email is galaxy@mainthestate.edu. Thank you.
Thank you.
My pleasure.
Thank you.
You're welcome.
Thank you.